Good morning, everybody. Welcome for another seminar from the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk Astronomy with Neutrino Telescopes by Dr. Agustín Sánchez Losa from the Instituto de Física Corpuscular-CSIC in Valencia, Spain. Agustín will be properly introduced by Dr. Rubén López-Cot. Please, Rubén.
Well, hi everybody. So welcome here today, and it is my pleasure to introduce you to Agustín. So Agustín did his studies in the University of Valencia. He did over there also his master's, working on the Untitled Telescopes, and also his PhD, actually in IceCube, right? Studying transient gamma ray sources like active galactic nuclei, X-ray binaries, and so on and so forth. Then he spent 6 years or so in INFN in Bari, in the Instituto di Fisica, Nazionale di Fisica Nucleare in Italy, and then afterwards he came back and he's now working at Física again as one of these investigador distinguido of the Generalitat Valenciana at IFIC again, where he works on the calibrations analysis of multi-messenger astronomy with a large volume water Cherenkov detector. So Agustín today will be talking to us about, in general, about astronomy with neutrino telescopes. I guess he will not have any bias belonging to the Antares and K collaborations. But he will talk to us in general. Okay, so please, Agustín. Thank you.
Thank you, Ruben. Thanks to the Instituto for this opportunity. I can mention also that I work within IFIC in the group of Valencia experimental group of astroparticles. That is the Vega without an H, not like a high energy group of astrophysicists from the Institute of Astrophysical Andalusia. I will do a compendium of how the neutrino telescopes work and explain how the analysis can be performed in order to do astronomy with them. And then I will present the latest results, the most relevant results in this sense. So I divided it more or less in 3 steps, in 3 blocks this talk. So what is a neutrino telescope? The first idea of this kind of detector was proposed by Markov in the International Conference of High Energy Physics in 1960. We're proposing to use natural transparent media to monitor, to detect the Cherenkov emission of particles within that volume, in order to detect atmospheric modes, but also neutrino interactions of high energy. To reach the sensitivity for the cosmic neutrino flux, a volume of this detector should be of around a cubic kilometer. Many neutrino telescopes have been designed around the time. There has been many pathfinders. I will summarize a bit them. But the basic idea is you have a large transparent medium like ice or water, and you place there a three-dimensional matrix, an array of arrangement of photomultipliers to survey the light in this volume, having a kind of a tracking calorimeter. So with this idea in mind, regarding the size of this detector and the density of these light detectors within the detector, you will be sensitive to some energies or others of neutrino fluxes. In the case of neutrino telescope, this aim mostly to go from the GeV neutrinos to the PeV, IB, and EV, which correspond mostly to the atmospheric neutrinos and the cosmic neutrinos and the cosmogenic ones. So the atmospheric are those created by cosmic rays in the atmosphere of the Earth. Cosmic are those expected from cosmic ray accelerators and astrophysical sources. And cosmogenic is hypothesized to be the flux that could be resulting from the cosmic ray interaction with the CMB. Regarding the energy range, you can perform different kinds of physics. with neutrino telescopes at the lowest energies, MEV. I will explain how you can do that, but you cannot resolve MEV events within these detectors, but you can still try to detect them, so you can be sensitive to corpuscular supernova detection. Since for those events you expect like 20 MeV neutrinos coming from. Also at GeV energies, you can perform studies on the neutrino properties, like neutrino oscillations, and at higher energies, you can perform either studies of dark matter searches or exotic searches like neutralins and other particles, or astronomy. So I'm going to focus on this talk. So the link basically is that when you will have a cosmic ray acceleration in a detector, if it targets a medium, it will have hadronic interactions, and the resulting decays will provide a flux of neutrinos that will reach Earth and absorb it. Therefore, these are going to be used in correlation with gamma rays, but gamma reproduction can be due to many other reasons. So seeing gamma rays is not a clear hint that you have a direct hint that you have cosmic ray acceleration, but neutrinos is a clear proof of an hadronic scenario, so where you can have cosmic ray acceleration. So it has its interest on this side. On gravitational waves, also there are some models, so you can look for them. So the fluxes are not expected to be so high yet, but there are some limits that can be placed. So basically, we are just with neutrino telescopes for astronomy looking at from AGNs to microquasars, the galactic center, or even coming from supernova remnants, corpuscular supernova, and transients like merge of compact objects, gamma ray bars, etc. So, which neutrino telescopes are in the world? Yeah, so there have been like pathfinders that were first attempts to build up neutrino telescopes. The first one was Duman in Hawaii in the 70s, was not fruitful, but Baikal was managed to be one of the first built. It was built in the Lake Baikal in the 90s, same for Amanda in the Antarctic ice. Some Italian projects were attempted, Antares was completed, and I work there, so I'm going to focus also on the results of Antares. Currently, they are taking data IceCube, that has been completed a decade ago, more than a decade ago, ChemFinet, and Great Volume Detector in the Lake Baikal, ChemFinet in the Mediterranean, both in taking data in partial configurations as they are growing now. So the pathfinders, so like Antares, or Amanda or Baikal, were like a 1% of the IceCube, that is the cubic kilometer detector, and probably the most known neutrino telescope. And the ones that are currently taking data or even being built are going to reach that volume, the cubic kilometer. They have been planned for the following decade, start to build up another detectors like ChemFinet and IceCube. In the Pacific Ocean, P1, in the South Sea of China, has been announced Trident a few years ago, I think. And the last summer, Hunt and another project called Neon, both in China, were like presented in the International Cosmic Ray Conference, saying that they plan to do also another neutrino telescope detector. Hunt either on the Baikal or on the south of China. IceCube also is planning to do an upgrade Gen 2 that during the next decade or during this decade that will make it larger and more sensitive to even higher flux energy. So starting with IceCube, that is the most known neutrino telescope, is the largest ever built, and currently still is the largest one. It's buried 2.5 kilometers in the South Pole in the Antarctic ice sheet, and it's comprised of 86 lines of 1 kilometer 8, and in an hexagonal array, as you can see here, of 1 kilometer base, more or less. Ice at those depths are really transparent, but there is a dust layer at around 100 meters width, half detector, more or less, from some volcanic eruptions in the past that divide a bit in half the detector. It also comes with a more dense configuration for be sensitive to lower energies that is called deep core. And as I mentioned, is planned to be extended to reach higher energies. It also comes with an isotope array where he can try to use it to bet out ongoing cosmic ray showers and therefore the events that reach the detector. In the Mediterranean Sea, we have basically two infrastructures. One in the south of France, where it was Antares, and close by there is now one of the detectors of Conferenciante, and the other at the south of Sicily, where there is the other one. Antares, it was a Pathfinder, a 1% volume of IceCube, more or less, that it was intended to work only a few years, I think until 2014 or 15, I don't remember very well, but it has been working well beyond its expected due time with a minimum maintenance until 2022. So it has been taking data for 15 years. And this detector was comprised of 12 vertical lines of around 500 meters and spaced around 70 meters between them. Just an artistic view of Antares, because we cannot do a photo of this kind of detector, so it's a way to try to imagine how it looks. It was composed by 25 stories per line with 3 neighbor optical modules. And we have Conferenciante now, which is a two-site infrastructure with 2 configurations. In the south of France, close to where it was Antares, now there is a Conferenciante Orca configuration, which has a much more dense array, and it aims to be sensitive to lower energies. So it's mostly suited for studies of atmospheric neutrinos. And then at the south of Sicily, there's going to be the currently with 28 string, the large configuration for mostly astronomy purposes. That will consist in 2 building blocks of ½ kilometer 8 and around 1 kilometer of base, made each of those of 150 lines. These vertical lines, instead of have like individual photomultipliers, they have a composed photomultiplier technology, which gives a lot more of directional sensitivity. And this is more or less how. Sorry. It's because the video. So my apologies, but it's because the video automatically was reproduced with sound, and I couldn't. Can you hear me in the Zoom room?
Yes, no problem.
Okay, because I touched a bit the volume. Thank you. So basically, you roll the complete line within one of these circular structures. You place them in the bottom of the sea where you are planned to place the vertical line. Let them to touch the bottom. With remote operated vehicles, you connect to the junction box that connects with a cable to shore, where you can control if all the instruments have survived, are okay, everything is green light. So you can then release it and do the unfurling of the view, leaving in place the vertical view, as we can see in the video on the right. So, well, this is an artistical view of impression of Conferenciante, the forest of optical modules with photomultipliers. How can we use these these devices? So we are going to detect all the light within this volume of this medium. This light, we aim for detect the light coming from particles, charged particles, and we are going to be regarding of the particle that cross the detector sensitive to one or another in function of the energy of the particle. They going to have a different mean path. So as you can see here, the muons propagate much longer than showers. So you expect to see much more muons in equal amount of interactions than showers crossing your detector. So the statistics of your detector will be dominated by muon tracks that cross your detector. Those are happening at very high energies, and the statistic is very low. So you're going to be mostly dominated by muon tracks. Since you are the main source of data you will have, we are going to have muon tracks. You are going to see also muons coming down from cosmic rays in the atmosphere. So you have very several orders of magnitude larger than neutrino fluxes, downgoing muon fluxes from the cosmic rays, but they are going to be downgoing. So you will have a background of muons, atmospheric muons, that usually you are not interested if you are looking for neutrinos, that came from above. This means that you use these telescopes mostly looking upwards, since neutrinos will cross the Earth. If the detector is in the South Pole, you will have in this upward sky one region of the sky accessible, while for example the galactic center is not accessible as upgoing from the South Pole. While in the Mediterranean Sea, for example, you can look in the upgoing sky, the center of the galactic ridge and the center of the galaxy. When you go to higher energies of neutrinos, the Earth starts to become a bit opaque, and then you stop looking just only at upgoing events, and you focus mostly, your sky is mostly the horizontal sky. The kind of backgrounds you have, as I mentioned, one is the atmospheric muons that are coming from above to your detector. Those are going to depend mostly on the depth that your detector there is. So Baikal, for example, is very close to the surface. They have an important amount of downgoing atmospheric muons. IceCube, Antares, and Orca are at 2 kilometers depth, and Arca, that is at 3 kilometers depth, have less downgoing muons. This is an important background because, well, you don't recognize what is crossing your detector, but you just see light. And with the light, you try to attempt a reconstruction. And if by error you misreconstruct a downgoing track as upgoing, even if you cut only all the downgoing events, you keep only the upgoing, sometimes you will have one of those in the upgoing. So it's important that you take into account more quality in your analysis, so you can remove as much as possible this kind of background. Also, you have an irreducible background that is atmospheric neutrinos, but that came from everywhere, from the cosmic interactions in the atmosphere. But you can cancel. They will have a softer spectrum on the signal that you are expecting to look after. So you are going to do a statistical analysis in that. Also in water, you have two light backgrounds that doesn't mimic with this. One is the K40, so isotope that we have in salt water. Its beta decay will create enough Cherenkov to illuminate neighbor PMTs in these optical modules, it can be indeed used to do a relative calibration of these elements there. Also, you can have bioluminescent events which have a completely different evolution, and they last seconds instead of the microseconds of a event crossing the whole detector. Regarding how we can detect these events, we basically get photons hits in our PMTs, and we try to feed them. Regarding of the optical properties of the medium, the light, the Cherenkov light from the particles will arrive more directly to the PMTs, or more scattered, or they are going to arrive less or more regarding the absorption of the medium. So, for example, water is not as transparent as the ice in the deepest depths in the Antarctica, but well, still they have one layer, as I mentioned before, at a certain point where they have a very strong absorption of light. While the scattering is in the opposite. In the water, the light is barely not scattered. In the ice, it's much more complicated. There are many anisotropies and symmetries. It's depth dependent, and it's very complex. So indeed, in IceCube, they work in something called the ice model that is necessary to study better and to reconstruct better the events there. So basically, water is optimal for pointing accuracy, and ice is better for calorimetry. This sample, we can see propagation of a track light, Cherenkov light. Red is like early detection of the photons, so they are not scattered or anything. So red is good, and blue is like bad because the photons will arrive scattered from much later, and then your directional is much worse. Of course, we're speaking about light speed events in very large detector. The positioning and the timing of the measurements of these hits, it's crucial. I could do a seminar only about the calibrations that are taking place, but basically it's reduced unless that in electronics you need a control at the nanosecond level of the timing that you are registering and the positioning within around 10 centimeters. Which in the case of water, it's a bit more complicated because the medium is light, your lines are moving, and you need to do a real-time acoustic fitting, etc. Also, you can have an offset, a systematic in the energy scale calibration, but the fluxes of atmospheric neutrinos in these detectors overlaps with other independent experiments. Regarding this, there has been in the last years a revolution with machine learning techniques that are really improving a lot this event reconstruction in direction and energy, but it's very challenging. This is a sample of the two main topologies that you can have in a detector. You either have an event reconstructed as a track or as a shower. And also you can have the double band topology that it's very infrequent, mostly because you need very high energy neutrino taus to have the tau fly a node before decaying and separate the two pulses that are generated in both showers produced. So this is an example of how one of the largest neutrino events ever detected in IceCube will look like in Granada. So this is the layout of IceCube, like 1 kilometer per 1 kilometer. And this is an event called Big Bear that was a 2 PeV neutrino. There are like a few more energetics since then, but the record is like 10 times more, or not direct to 10 times more. So this is still one of the largest, most energetic ones. What is the angular resolution for a neutrino telescope? Well, it depends a lot on which data you select. See, if you have in your data an angular estimation of your error, and you select those with the lowest one, you will purify a lot your data and get a lot of remain only with events that have very low real angular error. So it's hard to establish like an angular resolution like in an optic detector, but indeed it goes like statistically. But it's in a typical analysis, you end up with resolutions below the 1 degree, especially when you go to upper energies to TeV and PeVs, where you stop to be dominated by the angular uncertainty from the kinematic angle of the neutrino muon produced in the case of the tracks. And you can really reduce a lot the angular error there. In the case of the showers, it's much more difficult to detect the direction. And also it can happen that if your detector is very small, when you go to higher energies, the showers are larger than the detector often, and then you cannot reconstruct very well the shower. So only on big large detectors, you can really maintain a low angular resolution. Regarding energy resolution, it's also the same. Depends a lot of the selection of data you do. In the case of tracks, it's hard to define like a standard of which energy we speak about, because you can speak about the energy of the muon, you can speak about the energy of the neutrino that creates the muon if that muon was created by a neutrino. The deposit energy in the detector typically is usually mentioned the energy of the muon when it was getting within the boundaries of the detector. In the case of showers, it's much better because they usually often are contained, and you can just measure the deposit energy with the detector. So for tracks, regarding the analysis, it can be between 30% and even better in some cases. And in the case of showers, it can be 5% or even better in some cases. Usually, when you perform astronomy or analysis of this data, it doesn't matter too much the accuracy or the precise accuracy of the energy of that event, but you rely on energy estimators that allow you to distinguish more energetic from less energetic events to try to distinguish signal from background. So this is a sample of public data sets along 10 years from 2007 to 2017. In red, you can see the public data set of Antares. And those are the events or the neutrino candidates that have been reconstructed by Antares and used for certain analysis. For IceCube, I only show the outgoing sky just to don't clutter everything in blue, but they also liberated the ongoing events. And you can also have a look at how infrequent or how special are typical IceCube alerts or the high energy certain events, sample of events of IceCube within the detector. This is just to give you an idea of how low is the statistics of these experiments and how in the brink of statistical, how in the edge of statistical significance we are when we perform analysis with them. How can you perform analysis? Well, one is looking for spatial correlations with these events, these neutrino candidates, where you can use the angular solution of your detector to discriminate it from the background. You can add also the correlation with the energy, since the background of these events is dominated by the atmospheric neutrinos that have a softer spectra than the cosmic signal. Or you can also constrain in time when you have a reasonable signal hypothesis with a transient event, where you really kill a lot of background when looking for signal. Indeed, you require like 2 or 3 times less signal for a discovery than without this assumption. And so you have generally 2 kinds of analysis. Those called binary, that is just cut and comb. You just evaluate the patterns expected in an area, and then you see when you see your data, you see the deviation from the expected background. Or you use the unbinary analysis that basically weight continuously the properties of this data sample. The kind of searches you can do, one are the diffuse searches. So you look just for an excess of neutrinos above the backgrounds. So looking for the cosmic signal. Typically, they are done just by looking in the energy dependence and looking the excess that you can have at the higher energies. But you can also looking for extended regions where you can, for example, in the Fermi bubbles, you can check if there is an excess just by comparing with expected background on other areas of equal exposure of your detector, or the same for the galactic reach, or even you can assume some morphology from some estimated emission model. For point source searches, when you look for cosmic neutrino sources, you can do an all sky search or full sky, where you are looking everywhere in every direction. What you see here are not events, but a significance map. So you can see like fluctuations from the background that some of them can be particularly significant. Those are the so-called hotspots, and they are particularly interesting when they are close to known sources. The advantage is that it's model independent. It doesn't rely on any assumption. The disadvantage is that they have a very large trial factor. You can, of course, just look to a list of candidates that are particularly promising sources of cosmic neutrinos. The advantage is that you reduce a lot the trial factor, but you start to be model dependent. And the next most constrained model dependent is what they are called catalog searches or stacking searches, where you just look at the catalog of a certain kind of sources, and you assume that a parameter of those sources are proportional to the amount of signal. So maybe some sources weight more than others, and you do a kind of joint analysis of all of them. That's very model dependent. And of course, you can do a lot of transient searches. You can just look for neutrino counterparts from gamma events, from other neutrinos in other detectors, etc. I'm going to now show some interesting results from the last years. And I'm going just to show the latest results or most significant results on neutrino telescopes on astronomy. So let's begin with the confirmation of the neutrino cosmic flux. So in 2015, IceCube already showed some excesses from the expected background. More than 10 years later, they are well beyond the 5 sigma evidence of deviation from the background in IceCube. for this cosmic signal. So you can see here, for example, this is the energy of the neutrino flux. This is the atmospheric component. This is the cosmic component. And this is the expected prompt component. So you can see that you have a clear excess of cosmic neutrinos coming from where? That's the next step. Antares, that was a 1% size of IceCube, more or less volume, managed to see some interesting fluctuations. Still, the latest analyses are going on. But as you can see, the expected flux of cosmic neutrinos are a bit in the edge of the capabilities of Antares to see some excess. When ChemTriNet will be completely built, it's expected to detect with 5 sigma significance this flux within half a year of data taking. Would like to speak a bit about this aspect of the data analysis in neutrino telescopes. Here you can see different data samples from IceCube that, as you can see, regarding the selection and how are they treated, they are sensitive to different energy range. So some are like more sensitive to higher energy neutrinos of the flux, and others to lower energy neutrinos of the flux. And each of them independently can have a preference in the fitting of the spectral index, assuming on a simple power law, flat power law, simple power law. You can find like different spectral index for different samples within IceCube, and also like different fluxes normalizations. This can explain that maybe instead to have just one simple power law feature, you can have a more complex feature in the flux, like a broken power law. On this regard, even probably Antares and other detectors that are more sensitive to lower energies can even give an answer to these kind of features. But we are on the brink, as you can see, of start to study these particularities of the neutrino flux. Looking not all the whole of the sky, but looking for neutrinos coming from the galaxy. Very recently, IceCube showed a very interesting fluctuation from the background in the galactic ridge. There has been analysis performed in Antares by looking in the same region, just with a contact cone, with a slightly interesting fluctuation that goes in that direction, and also assuming a morphology, a model emission of neutrinos coming from the galactic plane, the Kragan model. This is a detail of the IceCube significance map, where you can see how this is the galactic plane. This is the region of the largest excess that is responsible of that, the excess I mentioned before, of neutrinos coming from the cosmic neutrinos coming from the galaxy. The color gives a hint of the spectral index that is fitted, so probably like the hardness and the softness of the different sources. So it's very inspiring that there will be like different kind of sources responsible of these neutrinos. Also, it's possible to do a fitting on the flavor of the cosmic neutrino flux raving to detected. And so far, IceCube have managed to fit something that is compatible with the assumption of mostly 1-1-1 equal flavor at Earth that correspond to the more reasonable proportional of neutrinos at source, 1 electron for 2 muons and non-tau in the production. More going just to looking for sources, we can see that IceCube found that the most significant, one of its most significant spots, and it's with NGC 1068. There it is, with an interesting excess of 4.2 sigma. The searches, so when ChemTriNet will be fully built, it may be able to detect with 5 sigma significance this kind of source within 3 years of data taking. And in Antares looking for these sources didn't find those hotspot on NG 1068, but on MG3 distant here and 3C403. With some post trial that is still background compatible, but well, And these are the latest results on point source analysis in neutrino telescopes. Also, there has been performed catalog searches. As I mentioned before, you just assume a kind of astrophysical source of responsible for your signal. Has been searches on blazer catalogs on radio galaxies with some interesting overfluctuations from background. It seems that could be something there. I'm going to stop a bit to speak of this famous case that it was Texas 0506 that in 2017 IceCube emit so a high energy neutrino of those that we saw before emit an alert, and soon it was confirmed that it was compatible with the direction with the Texas source that was confirmed by Fermi and Magic that were on a gamma ray emission state in that moment. This created a lot of inspiration and emotion, because it maybe would be like the coincidence that they were looking to confirm one of the first neutrino sources. The IceCube looked in the archival data of that source to check if there was something interesting, and they do like an untriggered flaring neutrino feeds within all the neutrino that they got, and they found a very interesting neutrino flare, much more significant than that isolated alert, let's say, on a different moment. That is what this has been called an orphan flare, because we see here in black the gamma reactivity of Texas, the radioactivity. Here is the alert that triggered these studies. This is the period of the untriggered the orphan flare of neutrinos of IceCube, and this includes also an event of GBD that was more or less in coincidence with the radio flare. We have been looking with other detectors, especially neutrino detectors during this orphan flare, looking for coincidence. And well, we found one event in Antares. It was found one event that was compatible with that flare. Similar studies has been done looking for untriggered flares on significant, interesting sources, not only Texas, but also many other. And the IceCube collaboration released this set of neutrino flares that were found on their archival data on these sources, and Antares has been looking at the data, trying to look for some correlation of this, with this being one of the largest significance with Texas. This triggered a lot of attention, like looking for correlations from these high energy alerts from IceCube. Some of those were compatible with other sources. Some were easy to be compatible with a lot of them, that maybe well in a gamma ray emission state, etc. So there has been a lot of follow-ups, a lot of interest. Also in Antares and in Kentine, we are following up these things. And it triggers also a lot of looking for potential correlations of these neutrino events with other messengers, like tidal disruption events, etc. There was even a use of the public data set to look in a correlation with radio emitting lasers, which show some interesting insights and which justify a collaboration that has been using, instead of an old data set liberated from that detector, but by looking with all the data so far. Also, we have been following up, Neutrino Telescopes have been following up with those so far gravitational waves. This is like the last coincidence that we still are missing so far. There are a lot of programs that are following them up, even trying to, for many famous and particular gamma ray bars, even trying to constrain some neutrino emission models for those events. And indeed, there is people in my group that is working on this, and even study the ability of Conferenciante to put constraints on these things in case of a detection once completed. Many more analysis can be done via like combined analysis of IceCube and Antares, both datasets combined, looking for point sources or full sky. This has been done in the past. trying to compensate, for example, that the IceCube, the ongoing sky is for us the upgoing. So improving the sensitivity, especially on those declinations. And we follow up a lot of alerts like gamma ray bars, etc. Just to finish two more things. One, it's possible to detect collapsed supernovas on neutrino telescopes, but it's a bit tricky because you are not going to resolve those MEV neutrino interactions in the detector when it happens, but you will expect to see a sudden rise in the multiplicity of the triggering on the whole detector. So that's what is being designed and achieved and pursued in Conferenciante, for example, where they can detect potentially a supernova, a collapsed supernova in the neighbors of our galaxy. And last, I want to show something that we see, that are the sun and the moon, or more particularly the shadow of the sun and the moon, that they produce, blocking the cosmic rays, and therefore an under fluctuation of the ongoing muons reaching your detector. So this helps to the absolute positioning of these neutrino detectors. With this I end. Neutrino telescopes are working a very not traditional ways. Are a bit tricky to understand, but they can perform astronomy as long as they manage to reach the statistics, and they work on them. They have a reasonable angular resolution. It's clear that there are high energy cosmic neutrinos out there, so we are just looking for when exactly they are coming, which kind of neutrino sources are out there, and probably we expect that many of those things will be clearly answered during this decade. And more neutrino telescopes are coming in the way with that complete the sky coverage and that also allow to perform independent processes, which I think is really, really important. And there are many hints that there are a rich and very diverse neutrino astronomy out there. This taking into account the fact that the multi-messenger astronomy helps you to look at the particular moments and reduce the background, makes that probably the cooperation with other observatories doing this kind of multi-messenger cross checks, you may be able to see the signal even before than a time integrated search or a weather integrated search. So I believe that especially in this decade and the next one, there are exciting times ahead for neutrino astronomy. So thank you for your attention.
Okay, thank you very much, Agustín, for this nice overview about neutrino astronomy. And now questions, Agustín.
So thank you very much for the very nice talk. I was wondering about the catalog searches or catalog connections between AGNs and the neutrino events. Which catalogs have you used so far? Because in the presentation there's possible connection between radio flares and neutrino events, but have you considered catalogs in other wavelengths like the Fermi catalogs, for example, in gamma rays?
So regarding the catalog searches, well, me personally I didn't work on them because the most similar thing is that I look, for example, for blasters that have very strong variability, since I work mostly on time-dependent analysis. So what I did myself was to take the Fermi catalog, for example, check the blazars with the strongest emission, the largest variability, and do kind of a ranking, and then get one of those and study the flares of those flow sources. Catalog searches that I use, I don't know exactly all the details. If you are looking for the correct reference of those, and every analysis has a different one. But I know there have been following safer galaxies, radio galaxies, For blazars, I understand AGNs very, but also from radio blazars, because well, there was this shift in the interest since it seems that in correlation with gamma phase it was not clear. A hint there after looking so much, maybe it was on radio, so people start to drift from interest on these kind of catalogs and searches, so they build up radio bright blazars and looking on those flares, etc., etc. I don't know if I'm answering your question or
Yeah.
okay, fine. Thank you.
You have this slide with the percentages of AGNs, TDs, and so on, right?
Percentage of AGNs, do you maybe refer
Yeah, this one.
to this thing here?
Yeah, so here.
Yeah, this was a study. We're trying to guess the whole flux of IceCube, the excess that the cosmic neutrinos that IceCube see. I mean, you refer this here, right?
Yeah.
Which kind of sources could be responsible or contribute up to how much? Indeed.
Okay.
And for blazars, indeed, it was for AGNs was say constrained to be a contribution below the 30% of the total flux. So that's what that was the conclusion of that analysis.
Was that study performed like theoretically or phenomenologically, looking at the neutrino events coincident with AGNs, TDs, or whatever?
I think it was an independent study, and it was not done with the low-level data of IceCube or something like that. It was something. Maybe there is someone that knows.
No, I mean, I think it was inferred from a result from IceCube, from paper dedicated from IceCube, and what is the limit that you can see from AGN or whatever. And these people just made estimation based on.
Okay,
Thank you, Pablo.
all right, thanks. Any more questions?
Maybe I can also comment on the previous question, right? You know, the catalogs that we were testing actually in the right blazer, we were discussed together with radio astronomers, with Yuri Kovalov, actually, that is observer. So these BLB blazers were, they were helping us to construct the catalog and where to look. Basically, there was like some cut in the mission and then so in this particular study, it was like 2,000 objects that we were looking on.
Okay. I have a question. Can you go to slide 23?
This was this one?
Yeah, this one over,
Yeah.
this one over here. So I wonder what is the difference between the angular resolution that you get for muons and electron neutrinos coming from, because the one from so over there for K3net, you're supposed to be as good as
Sub degree.
yeah,
About TV. Yeah.
sub 0.1 degrees, right? For muon neutrinos.
Those are the expectations.
For electrons, you still get
A bit worse.
What is the reading of this?
Well, basically, let's say that when you have a track, it's much more easy to how to say to get the direction, because you have along your full detector a lot of points in time that give you a lot of say leverage. While in the shower, you rely on the evolution of the shower, how it is boosted in one direction, which is not so clear as in the track channel. So the main difference why it's harder in general to get a good directionality in showers or cascades is because you rely on the boosting of the evolution of the shower to detect the direction. And that usually it's not as clear than when you got a track crossing your full detector, where you have much more. That's the main reason why it's worse usually in showers.
And the comparison between you that are operating in water and IceCube that is operating in ice is that
well, this came from this explanation mostly here.
yeah.
In ice, you get a lot more of scattering, so the it depends on the amount of light you get from the event. So if you got a very energetic event, you will probably have enough light to even constrain very well. But if you don't have so much light, most of the photons will have been scattered already at different times to your sensors, and it will blur somehow the track passing through it. So that's why usually a medium with a more scattering is worse for angular resolution than a medium with less.
But also for showers, right? So in IceCube.
Yes, on the directionality, yes. But the good thing of the ice is that the absorption length is much lower, so you get more energy detected from the interaction. So you are better on estimating the energy in ice in showers than in water, in principle. Probably it will afterwards it will depend on the sense of your detector, how well you treat your data, how much you improve the selection, etc. What are the algorithms? And currently there is a revolution on this because, well, there is GraphNet and all this community working in graph neural networks for the reconstruction of tracks, also of showers. Indeed, IceCube improved significantly previous analysis by introducing deep neural networks on the energy estimators of the showers. And well, it's during this decade there's still a fast evolution of how these graph neural networks can improve your angular resolution by fitting your data.
And regarding the calorimetry, can you have problems with very high energy events? For example, the one you have in your previous slide, or the one in which you have Caramel. One of these very big. Yeah. So this one in KM3net, it would be.
No, it will fit perfectly because KM3net maybe is half height, but it will be 2 blocks of the same base, 1 kilometer, 1 kilometer. So if it happens not there, but there on a equal size, so it's, let's say that in a fast way approach, IceCube is like if you cut this half and then you push it besides, let's say, a bit. So no, you will see it because KM3net will be that large, that big. Currently it's under construction, so it's a bit like Antares, where you are small, and an event like this you will not have it completely contained within the detector. But that's because of the size. KM3net will be able to fully contain this kind of effect of events.
Okay, thanks. More questions?
Short one. My question is if there is an alternative to lasers to explain the galactic neutrino flash, mainly just because I mean the studies that you have shown are not highly significant, and even in the case of TXS 0506,
there has been a shift between going from laser to looking something like radio galaxies or safer galaxies, or because it's reasonable that maybe you are going to see neutrinos mostly on accelerators where the accelerator is completely obfuscated by the medium, where you got a lot of dense target media, you can get a lot of neutrinos coming from. So instead to see a clear gamma ray activity, you get all that container, you don't see that, but you see the neutrinos. So that's the case for NGC, that it's not it's not a gamma ray activity laser. It's
I think it's a safer galaxy or something like that.
Safer galaxy. And yeah, it's in
1068, isn't it?
NG 1068, yes. Yeah. So yeah, especially when this came out, people start to look even more to potential models of neutrino production on this kind of galaxies. So like, okay, we don't have a gamma ray clue about it, but maybe how can the neutrinos be produced because of this? Maybe the gamma ray get absorbed and you only see the neutrinos coming out and these kind of things.
Are gamma ray bursts also a candidate?
There are models with some expected neutrino flux and some conditions, but so far has been no evidence or something like that. Indeed, during the last decade, I remember that the models have been constrained even more and more and more by the lack of evidence or excess on that.
Correlation.
Okay, any other question, Agustín? Well, otherwise, we thank him again.
I don't know if in the chat I didn't look. No question. Ah, okay. Sorry, I forgot to repeat the questions, but I expect that the answers and make understand the question. Sorry.
It's all right.
Okay.
Thank you.